Welcome back to Mechanics and Control of Robotic Manipulator. This particular lecture is actually a continuation of robot differential kinematics. So you have seen so far position model, then the velocity model. That too, like velocity propagation model you have seen in the last lecture. This is supplement to that particular lecture where you would have started talking about differential kinematics in the two subsections. You would have seen one is forward differential kinematics, the other one is inverse differential kinematics, where I will just write the equation for your benefit. So this is what you would have obtained as forward differential kinematics. So there is another case where q dot you wanted for given mu dot. So then this is actually like inverse differential kinematics, right? So this is what we have seen, and in inverse differential kinematics you can call it as controlling the manipulator, but that is open loop. But in this particular short session or the supplement session, would be seeing more about the closed loop session. In the sense, you can see that this manipulator can be controlled with respect to this end effector point. In the sense, I want to follow certain profile, that also can be obtained, or this control can be done with the joint space. So individual, you can say joints we are trying to control. In the sense, what you can see, so you can actually like directly see mu desired and mu desired dot, and I can try to find what would be the joint space velocity. So this is what I call task space control. Whereas the other way around, the mu desired and mu desired dot, I derived as q desired and q desired dot. And then I'm trying to control, or I try to calculate what would be the joint space, actual joint space velocity. So this is what we call, you can say, joint space control, and this is what you call task space control. In the sense, in the differential kinematics also, we are still mapping operational space variable to the, you can say, configuration space variable, or configuration space variable to, you can say, operational space variable. That mapping we are still doing it. Then what the benefit here is actually like we are trying to control, in the sense, for example, I am just saying that the mu desired, in the sense this point supposed to be, I assume that the workspace is actually like reach 1 meter cube. I'm saying that my end effector point supposed to maintain 0.5, 0.5 and 0.5 in all three axes. That is within the workspace, and the mu is actually like achievable. Can I actually like make it for a given time? Can I actually like make it? So one simple thing will come whenever you talk about the control. So one of the important thing will come, in the sense the control would be having two things, two purpose. One is the stability, because this robotic manipulator in dynamics, it is actually like unstable system, but in you can say kinematic level, it is still stable system, but you can see that the stability is one concern, the other concern is actually like performance. So right now we are actually like talking about the kinematic, you can say, control with respect to stability. Then we can actually like increase the performance, in the sense, so how you can actually like minimize the error, and how fast you can achieve the response, so how you can make the stability, or you can say settling time faster. All those things will come into second stage. So right now we are interested to see the stability aspect. So in the sense, what we are going to see in this particular short supplement session, you would be talking about the kinematic control. So in the sense, what we are trying to see, we are trying to see the configuration space or task space, or joint space control, or operational or task space control. In the sense, here the q desired and q desired dot would be obtained. That would be obtained from the mu, okay, and you are looking for q dot, and in the task space control, mu desired and mu desired dot are given, and you are actually like trying to see the q dot directly, okay. So in the sense, I just wanted to show one flow chart. So this is what your robotic system, okay, and what you are seeing, that the q dot as a feedback, okay, and you have mu desired and mu desired dot are the user input, and from there you are taking an inverse kinematic model, okay, and you are actually like seeing that the q desired dot or q desired, so these are actually like obtained, and you are actually like seeing that, so not q dot, this is q, and you are actually like trying to compare this, in the sense you are actually like getting it, I'm just rubbing it. So you are actually like, I'll see this is, so I'm saying that from this you will get q desired dot and q desired, then I'm taking a feedback. So in the sense, I'm taking this and I'm seeing that what would be the error, that is q tilde, which is q desired minus q, and this is actually like I'm putting as a proportional or some controller, and this controller will take the, you can say, response, or you can say the detail from the Q decide dot, and this is actually like going to give the Q dot. Okay, so this is what we are actually like seeing it, in the sense what you are giving, your robot would take a input as Q dot, and you would be integrating, that is what your robotic system will do, that will give Q. This is what the configuration, you can say, space control, whereas the other way around, so your robot will give Q, like take input as Q dot, and that would take as output as mu, and that mu you are actually taking it as a straightforward, as a feedback, where mu decide is given and you are taking a feedback. Okay, and then you are actually like taking the mu, you can say, decide dot, and you are actually like adding these with the controller, and the controller is giving Q dot. So this is what you are actually like seeing everything in the task space, and then we are actually like trying to see what would be the joint space velocity would be sufficient to fulfill the you can say tracking performance. So in the sense what we are interested to see the joint space control first. So in the sense what would be known or given, the user input would be, so Q decide and Q decide dot, right? So these are actually like given to us, in the sense joint space, so positions and joint space velocities are given. Okay, now what we can actually like see from system which is actually like available, the Q would be available. Further, I assume that the J of Q also like available, in the sense what I'm saying, the actual joint positions is available and Jacobian matrix also available. So now what I can do, I can actually like see what would be the case, the joint space velocity can I obtain. And since I said the first premost important thing, I am actually like trying to see when t tends to infinity, my Q tilde, which is nothing but Q decide minus Q, can go to 0. Okay, so then what I'm getting, the Q tilde as one of the choice. So the Q tilde supposed to goes to 0 when t tends to infinity. Was the easiest choice? The asymptotic, in the sense exponential function. I took exponential function with some positive constant, but that would be negative power, so where k is positive, and with respect to time what I will get, the t tends to infinity, so this Q tilde tends to 0, right? In the sense this would be equivalent to 1 by e kt. So this become infinity and 1 by infinity becomes 0, right? So this is what the case. So now I am actually differentiating this. What I will get, so Q tilde dot is equivalent to minus k into e minus kt. So in the sense minus k, so Q tilde. So in the sense I put it everything one side, so Q tilde dot plus k, so Q tilde is equal to 0. Now what is your interest? Your interest to find Q dot. So what is actually like Q dot? So Q dot I can actually like get it with the other way around. So now what I'm saying, this Q tilde dot I can write as, this is the differentiation. So Q dot decide minus Q dot. So I'm substituting that here in this equation. What I will get, so Q dot decide minus Q dot plus k into Q decide minus Q equal to 0. Okay. So now what is my interest? I want to find out Q dot. Then I can see that remaining everything I'll put it one side. So then the Q decide dot plus k into, so Q decide minus Q. So this is actually like simple first order differential equation, and based on that you can see that the user input, or you can say controllable input, is like this. If you know Q decide dot and Q decide, you can actually you can get it. And this is a simple proportional control, in the sense it's a simple feedback with a proportional gain, and this is a simple feed forward term, right? So this is what you will get as a simple computing velocity control. Why it is computed velocity control? Because you are computing the velocity which is supposed to be given as a user input, that is you are computing with respect to your desired velocity, which is nothing but a feed forward term, and you are actually like seeing from the feedback. Now you are actually like seeing only point to point. Then you can see that what would happen, the Q decide of time is actually like simply Q decide, which is constant, then the Q decide dot becomes 0. Then you can see it's a simple feedback, in the sense Q dot is nothing but, so k into Q decide minus Q, right? So this is what you will get it. So now imagine, so this is not the case. I wanted actually like a task based control, in the sense the known is actually like mu decide and mu decide dot is given. So these two are known and given, and this is actual joint position, and you can say actual task space position are known, and the Jacobian matrix is known. I can get it. So already I know the mu dot is nothing but j of q into q dot. So in that sense, I can see the task space velocity in this way as long I know q dot, and I can get it. Right? This relation you can feel it, and now we will see in the next equation how that would be useful. In the sense, what we are doing it in a task space control, these two are given. In the sense, mu decide and mu decide dot is given, and we are actually like going further. So what I assume that, so the exact task space position is not easy to get it, because you have to use some inertial or some camera to find it, but actual joint position is easy to get it, and forward kinematic model is unique in serial manipulator, and this relation is easy to obtain. In the sense, the mu I can get it with the help of the actual joint position, and Jacobian matrix also I can get it. In that sense, what I can see, I can actually like see mu I can get, and mu decide I know, right? So this is what I'm calling mu tilde. Okay, so now what is my interest? I'm interested in to find q dot, but what q dot? So q dot is nothing but j of q inverse into mu dot, right? So now we will try to find out mu dot. So mu dot is like this. So I'm taking mu dot decide minus this is nothing but mu tilde dot. So as similar sense, the mu tilde I'm taking as, so mu decide minus mu, and taking a differentiation, this is what will happen, and this is what the error, this I'm choosing as an exponential function, which is I'm assuming as this is k into t. So now what will happen to mu tilde dot? So this is mu decide dot minus mu dot, this would be minus k into e minus kt. And in the sense, what happened, mu tilde dot is nothing but, so minus k into mu tilde. So then mu tilde dot plus k into mu tilde becomes 0. And you can substitute that. So mu decide dot minus mu dot plus k into mu decide minus mu is 0. And from there you can actually like find mu dot. So mu dot as, so mu decide plus k into mu decide minus mu. This is mu decide dot and this. So now you substitute this here, what you will get q dot as the earlier case, right? So now you can see this is what you are computing the velocity of individual actuator, but with the help of the direct operational space variable. So that's why it is called task space control, and as long this k is positive, so both task space and operational space is achievable. And further I want to give here, so here you can see that this is a simple proportional control with the feed forward term, but in the modern days, so this actually like evolved with the learning base. Why? Because this is t tends to infinity, the mu tilde tends to 0, in the sense mu of t tends to mu decide when t tends to infinity. But I want t not taking infinity, it is some finite time can I get mu tilde to 0. And the mu tilde range also like I want certain range. So in the sense I am putting so many, you can say performance characteristics, can I get it? So this is very easiest one. When I keep on increasing the k, so I will see that the convergence would be faster and faster, I agree. But if I apply other, you can say non-conventional control, in the sense sliding mode or learning based control or neural network based control, I can actually like get it much more better than this. So in the sense, what we can see in the modern control also coming into a picture on the robotic manipulator control. And further in manipulator theory, the kinematic control is not so popular. Why it is so? Because so the manipulator is in 3-dimensional space, and obviously the manipulator is a huge, and inertia is involved and gravity is involved. You cannot make it as a simple, you call kinematic control system, or in the sense the system dynamics is simply realized in a kinematic level is not possible. So in the sense, in robotic manipulator, motion control means it is a dynamic control, and force control means dynamic with motion control. That and all we will see in the fourth phase of our course, in the sense the motion control of manipulator. Right now I am just giving a simple supplement, since we talk about what you call inverse differential kinematics. So there I told that it is controlling the manipulator, so I thought I can address what is kinematic control. So that's what the supplement all about. So with that, I am actually closing this particular session. So we will meet in the next session, which is on statics of robotic manipulator, and then we will move forward with the dynamics and motion control. So with that, I'm saying thank you and see you then. Bye bye. Take care.